Good morning, as Dr. Grajan said, we are Design Team 3. My name is Nate Kesto.
My name is Sabor.
My name is Charlie.
I'm Mike Mark, and you are Nate.
And our presentation today is on filter design and applications. So here's just a little outline of what we're going to talk about today. I'm going to give a little introduction on the filter types and the characteristics. She will talk about some of the different filter designs, specifically the low pass, high pass, band pass, and some of their characteristics. Charlie will then delve into the differential filtering example. I will then give you an example from our design project on power filtering. Mike will go over an audio application, followed by Yuan with a band stop example on application. And then Justin will conclude with an ECG application. So filters can be characterized as being either analog or digital, they're passive or active, and linear or nonlinear. The different filter types are low pass, high pass, band pass, and band stop filters, or notch filters. I'm going to pass it over to Shia, who's going to explain some of these different filter types.
In filter designs, I would like to talk about odor and the color frequencies. The odor of filters will significantly determine the stiffness of the stop band attenuation. For the first order filters, it has 3 dB roll-off, which means its slope is 20 dB per decade. But for the second order filters, the stop band roll-off will be twice the first order filters at 40 dB per decade, which is 6 dB roll-off. And for the third and even higher order filters, the changes, the increases are defined similarly. In general, the final rate of power roll-off will be for the order N output filters is the 20 times N dB per decade. And the color frequency is also a main characteristic for the filters. The color frequency is the where filter attenuate the input signals by 3 dBs. And for both the LPF and HPF, they both have only one color frequency, but for the bandpass filter and notch filter, they both have 2. And the equation we show on the PPT is the color frequencies of first order filters, which is 1 over 2 pi times time constant. Time constant is dependent on the type of circuits. In this one, we can see time constant is R times C, so we know this is RC circuit. For example, if we want to use the RL circuit, the time constant would be L over R. And the color frequency is R over 2 pi times L. And this is an example of first order passive low pass filters. I just use the TINA TI. I draw this circuit by using the TINA TI by using the RC circuit. This transfer function in frequency response is V out equal to 1 over 1 plus j omega times C times R times V input, which we can see it only has one pole, so we know it's first order filters. And the figure below is frequency response body plot. And we can see the flat band below the color frequency is the pass band, and the part where the signal is above the color frequency is the stop band. And this is the first order active low pass filters. And we can see the transfer function is different from that of the passive one, because in the active filters we use the op-amp. And because the filter is active, it may have non-unity pass band gains. And if we look at the transfer functions, we can see there are 2 more parameters, which is R2 and R1, and the negative ratio between R2 and R1 is the pass band gain. And this is the example of first order passive and active high pass filters. And if we look at the body plot, it's just the opposite of the low pass filter. The bandwidth of bandpass filter is the difference between the lower color frequency and the upper color frequency in continuous set of frequencies. And on the body plot, we can see the frequency between the FH and FL is the bandwidth, and in the middle, where we call it the center frequencies. The most of the time when we talk about bandwidth, we also need to consider the Q factor. The Q factor is just a dimensionless parameter that characterizes the resonator's bandwidth related to its center frequencies. In other words, Q factor is the inverse of the fractional bandwidth. The high Q filters will have the narrow pass bands, and the low Q filters will have the wide pass bands. These are relatively referred to as the narrow band and the wide band filters. And this is the example of first order passive and active bandpass filters. for the passive bandpass filters, for the schematic, if we, for the schematic, it's just I just use a first order low pass filters connect to a high pass filter to come up with the first order passive bandpass filter.
Okay, after introducing those normal types of filters, I'm going to introduce you guys the differential filter. So what is a differential filter? A differential filter is any filter that takes differential inputs and gives differential outputs. And what is a differential signal? As we know, when we measure voltage signal, we need to give a reference point. Usually it's ground. So if one of the signal terminals are grounded, it's called a single-ended signal. And if neither of the signal terminals are grounded, it's a differential signal. Why do we need to use the differential signals? Actually, in real world, there's many differential signals. For example, in our project, the ECG signals we get from the thumb pads are differential signal. We want to differentially amplify them. If we use normal types of filters before the differential amplifier, that will lead to a reduction of the common mode rejection ratio and thus introduce more noise and interference. So the purpose of using differential filters is to increase the common mode rejection ratio and then reduce the noise and interference. So there's some examples of differential filter. You can see from the passive high-pass differential filter example, the right end of the circuit is a differential amplifier. This is how they interface each other. You can find from the last slides is that all of those filters are symmetric. So why is that? I'm going to introduce, the reason is of the process of designing that. This is an example of the designing process of a differential filter. So the first step when we design a differential filter is to design a single-ended filter which meets the requirements such as the bandpass, bandwidth, center frequencies as the one we need for the differential filter. And then we sort of duplicate another circuit and combine them around the ground point. After combining them, we need to take off the ground point, and then see in the example, in the middle, in the center capacitors, we take off the ground and then make them in series, so that leads to equivalent capacitor which has a value equals half to the original capacitors. Do the same thing for the load end. It will has double the resistor for that. So if we simulate the design differential low-pass filter, we will get the same result as the one we had of the single-ended filter. This is the low-pass filter simulation result.
So I'm going to explain filtering in a power application. Specifically, our design project calls for a 9-volt battery to be stepped down to 5 volts for use in the rest of our circuit. To do this, we decided we chose to use a buck converter, specifically the model TPS62120. This is a switched mode converter, so it's very efficient. However, it does generate a lot of noise. As you can see by this graph over here, the noise ranges from the microvolts to millivolts, and in some applications that can be very significant, including ours, which is measuring ECG signals. So that could significantly affect our circuit. And then to solve this noise problem, we decided to implement a low-pass filter. Here's a schematic for our power supply. We have the 9-volt battery going into the buck converter where it gets stepped down to 5 volts. And then the 5 volts gets voltage divided to 2.5 volts for use with the rest of our circuit. And then here is our low-pass filter right here. And then here I ran a TINA TI simulation with our filter. The cutoff frequency is at about 16 kilohertz, which is where a lot of the significant noise occurred. And then here are our results. As you can see, both channels are on the same scale. Channel 1, which is this channel right here, is the output of the buck converter, and it shows the switching noise of the transistors, these little spikes here. So we have 5 volts on the output of the buck converter, and then when we run it through our filter, we can see that the noise gets significantly attenuated, giving us a cleaner signal for use with the rest of our circuit. And then I'm going to pass it over to Mike for an audio application.
So after going through some of the backgrounds between different filter types, another common example for an application involves audio frequency ranges. And most people, when you go to a commercial audio store or something, you can buy a pair of speakers. A typical speaker type is a 3-way speaker that has different speakers that end up driving different frequency ranges to listen to them. So a way that this is actualized is by developing what you call a crossover network, which is essentially 3 different filters that take an input signal that's common to all 3, and then they output different frequency spectral content to each speaker. The reason this is necessary is because it's really difficult to design a driver or a speaker that can play all frequencies across the audio band. This is a typical example of a Bode plot showing the 3 different outputs for each crossover network. And then there's 3 different kinds of speakers, like a subwoofer, which handles lower frequencies, a mid-range, and then a tweeter, which handles high frequencies. Another common design challenge for doing a crossover network is that you have to keep in mind that a speaker's impedance is complex across a frequency band, so it's not necessarily a purely resistive load. And so you have to take that into account when designing a crossover, in that at different frequencies a speaker might have a 2 ohm impedance, like over here on this plot for impedance versus frequency. You can see at low frequencies it's about 2 ohms, and as you go up into higher frequencies, there's different resonant points, and then as it rolls up even higher, the impedance starts to climb out at higher frequencies. This is an example of an equivalent circuit for a loudspeaker. So if you're using a program like TINA TI or some other simulation package, you can measure the actual characteristic values of your inductance or your non-ideal capacitance within your speaker to then help you design your crossover. So the ultimate goal is to match your crossover with the natural frequency response of your speaker and also maintain appropriate power distribution through each of the 3 speakers so that you have an even representation of your music across the entire audio band. This is an example of an actual 3-way crossover system, just the schematic, and then this is an example of what one would look like if you were to buy one, or rather than buying one, we're all engineers so we can make our own. So pretty much not that complicated after we hear about the LC networks that Shu was talking about, or the RC networks. So as you can see, to drive a tweeter, you use a 2nd order LC high pass filter, and the mid uses a 2nd order low pass filter, and before that actually you put a capacitor, which also limits the low frequency noises. And the subwoofer, you essentially just use a choke to just make sure that the attenuation of high frequencies happens naturally to the subwoofer.
Next, I'm going to talk about bandstop filter. Bandstop filter is a filter past most frequency, but it attenuates a specific range of frequency to a very low levels. Notch filter is a bandstop filter with very narrow stop band, which means it have very high Q factors. The reason we need a notch filter in our design is we have maze hum, which is 60 Hertz power noise. So we have two choices. First choice use analog design, and another choice is digital design. For analog design, it's just simply summing of the high pass filter, low pass filter with IRC component with the optional amplifier to control the gain. For the digital design, we simply write the algorithm into our Stellaris microcontroller when we're doing the signal processing. So we choose to use the digital design for even, although the analog design is faster, but it is less stable and less programmable than the digital design. Also, another reason is for the notch filter, it had a steady effect. If the voltage gain slope is less than minus 40 dB per decade, the signal will be distorted. So to make sure our notch filter works, we choose to use the digital design. For the picture above is our ECG signal, and second picture you can see on 60 Hertz we got power noise. So in this case, we use MATLAB to do the first simulation. If it works, we can convert to C code and upload and programming our microcontroller. You can see from code we set up the notch frequency at 60 Hertz and the Nyquist frequency, do the sampling rate, and do the calculation. This is our algorithm. So this is a plot of a notch filter. So it has a very narrow band at 60 Hertz, and the slope is what we expected. It's much larger than minus 40 dB per decade. So after we combining them to our input, you can see the ECG signal is much cleaner, and the 60 Hertz power noise is eliminated. Next, I'm going to pass to Justin.
All right, I'm going to talk about our application of these filters to accomplish our goal of getting the ECG signal. So our overall analog front end is supposed to come out with a bandpass that has a lower cutoff of 0.7 Hertz around there and a higher cutoff of 50 Hertz because the spectral content of ECG signals is within that area. How we accomplish this is that on their input we have passive RC networks that have, including a differential filter, low pass, and then for our servo loop we also have an inverting low pass. The post filtering is an active low pass also, and then the right leg drive is an inverting high pass. Now how this works is that to get most of our filtering done before we amplify everything, we want to cut off as much as we can for the input filtering. And then the output of the INA goes to the servo loop. It is inverted, and then low pass is passed back to the reference pin of the INA, which will cancel out the low pass or the DC drift and any low frequency noise that we have on our signal. So therefore, this together will create a high pass filter because it will cancel out all the low frequency noise. After that, we have additional low pass filtering so that we can cancel out any more possible noise that we can cancel out. The right leg drive takes the output of the common mode signal. The way to set the gain on the INA is with a common mode, a resistor between the two amplifiers inside the INA, which will, at the center, if you split it with two resistors, will give you the common mode. You take that, you invert it, and put a high pass on it. You can send that back to the CardioSim. That will set the potential of the CardioSim on the body, whatever it may be, and you can send back inverted high frequency noise to kind of try and cancel out that signal when it gets sent into the circuit itself. Also on the Stellaris would be our digital filter to have a notch filter, which would cancel out more of that 60 hertz noise that's introduced by power systems. More detail on the Super Bowl loop is that it's an inverting high pass filter, low pass filter, sorry, but effectively going into this reference pin will create with the INA a high pass filter. Creating and adding those together will give you our overall band pass filter, which will achieve our goal of getting the spectral content from about 1 hertz to 50 hertz, which is our ECG signal. And that's it. So any questions?
Are there some questions? No questions.
All right.
Thank you. We'll have Chief Moore next.